many people here say, when asked about jokes, say, oh, darn, I just heard a good one, and you find out that you forget all the jokes you hear. And when it's your turn, you just can't remember. Isn't that true? Now, let me ask you a question. Which jokes is it that you remember? The ones you hear or the ones you tell? The ones you tell. If you want to be good at telling jokes, when you hear a good one, find a friend quick and tell it. Because once you've articulated it, once you've brought it up to the, to your verbal level, then it becomes like a part of you, and you can remember that, can't you? So that's why it's important when I say talk to your neighbor to really talk over the ideas, even if you already know them. Talk about the ideas. When you leave here, you go outside the classroom, talk about the ideas of physics with friends, okay? If you talk about those ideas, then they're going to become a part of you, and you'll find you remember them a lot more. You remember what you talked about, not what you heard about, Okay, let's begin. What are we going to talk about today? We're going to talk about the idea of inertia. Inertia. Heavy anvil here has a lot of inertia. If this anvil started moving, maybe moving across the table, you would look for some kind of cause, wouldn't you? Or if this anvil started going up in the air, you would look for some reason for that. In these days, we know there are reasons for things. And whatever the reason might be, you would label it some kind of force. Because you know this anvil not going to start going up in the air unless a force acts on it. Or it's not going to start sliding across the table unless a force acts on it. And so strongly embedded is the intuition that force is responsible to motion that years ago when the early Greeks were developing the ideas of science, Aristotle made that one of his dictums. And he said, hey, if things are moving that aren't supposed to be moving, well, we said the stars and the planets, those are supposed to be moving. But if things are moving that don't ordinarily move, you can be sure of one thing, gang. There's a force responsible. And that became like sort of a law of physics, that motion is associated with forces. No forces, no motion. Well, then about the time of Galileo, people were starting to question that because ideas came up like this. How about a cannonball? When a cannonball is fired from a cannon, it's easy to identify the force that gets that cannonball started, isn't it? It's the gunpowder exploding, isn't it? Does no gas explode and push that ball right out the barrel, huh? That's easy enough. But the question was raised, hey, once it gets out there and the expanding gases no longer act on it, what keeps the cannonball moving? So strong was the idea that a force must be responsible that people started thinking about things like this. Well, when the cannonball moves through the air, it's going to part the air in front and leave a vacuum behind. Now, there was another little law. It says, nature abhors a vacuum. So there's not really going to be a vacuum tube left behind. That air that's been parted is going to squeeze back down and fill it up, isn't it? Now, you've taken a bath with ivory soap, okay? Floats, okay? Do you ever be in the bathtub and you start to grab the soap and what happens? It keeps going away from you? It was thought in the same way that the cannonball is being squeezed by the air behind, and it's the squeezing of the air that provides the force to keep it going. What do you think? A fellow by the name of Galileo turned the whole thing around. Read about Galileo's experiments with the inclined planes. I won't talk about that now. But the gist of it is this. Galileo discovered that once something is moving, which might require a force, but once it's moving, if there's no friction, that object is going to keep on moving anyway, with no reason, no force required. And that property of things to persist in their state of motion is what he called inertia. Doesn't say why, but it's just a property of things to do that. So if an object is moving, no force at all required to move it, if there's no forces acting on it. Now, if this is sliding across the table, you have to keep pushing it. That's because friction acts. But if I put this on the ice, where friction were very, very low, and I got it going, do I have to keep pushing it? Does a hockey player today, in seeing a puck come by, say, ooh, what's pushing that puck? No, we know that something got it started, but once moving, it will move of itself. Now, inertia, mass. What's mass? What's weight? What's inertia? All the same? Answer begins with an N. No. Okay? How about mass and inertia? Just about the same. We say mass is like the measure of inertia. Inertia is the tendency of an object to persist in its state. If it's moving, it's going to keep on moving. You get in outer space and take a ball and throw it. If there's no forces acting in the ball, it doesn't slow down to a stop. It just keeps going, 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 going. If you have an object out in space and it's at rest, you leave it alone. You come back centuries later, it's at rest, as long as no force acts. That's the idea of inertia. Okay, watch this gang. Inertia, huh? Card. Coin, huh? Okay. A body at rest tends to stay at rest. I'll show you a nice one. Here's the one shown to me by my friend Marshall Allenstein. Okay. Get a little hoop like this. Balance something on the top like this. Marshall Allenstein. Okay. Here's a block of wood. Does block have any matter? Yeah, you can see it, okay? Have mass? To say it has mass is to say it has inertia. Right now it's at rest. Now what I'm going to do is I'm going to pull the tablecloth. I'm going to whip it. And when I pull that tablecloth, you're going to tell me, what do you suppose is going to happen to this block? One of three fates. Number one, recoils onto the floor. Number two, stays essentially where it is. Number three, follows along with me. Take a pick. Okay? Let's put it to experiment. And here we go. A 1, a 2, a 3. The staples provided the outside force that did move the block. But you know if there were no staples there, you know it. If there's no staples, what? These are not staples. This is for real, okay? Okay? What do you mean, oh no? You believe in physics? Have I not shown you that physics never fails? Let's try this. And a 1, and a 2, and a 3. Okay. What do we got here? Iron ball. Iron ball got a lot of mass. Got a lot of mass? Got a lot of inertia. Turns out if something has a lot of mass, has a lot of inertia, it also has a lot of weight. And people get mixed up between how much mass something has and how much weight something has. That's because they're directly proportional. We measure the amount of matter in kilograms, kilos. We measure the amount of weight in pounds, or in metric system, in newtons, newtons of force. 1 newton is about equal to a quarter of a pound, a little bit less than a quarter of a pound. So most of the world use a newton as a unit of force. Here in America, we still use a pound. But pounds, newtons, synonymous. That's gravitational pull. How many kilograms is what? How much matter? It turns out this ball is kind of hard to shake back and forth, okay? A lot harder than, say, a feather. And if I get out into a region of the universe where like all the gravities cancel out, gravity-free region, it's still going to be hard to shake back and forth. Because it still has the same amount of matter. It still has the same amount of inertia. But it might not have any weight. If you put this in a bathroom scale, no weight at all. Now I want to show you a demonstration which will demonstrate the property of weight and the property of inertia. Let's try it. What I'm going to do is I'm going to pull this lower string. And I'm going to pull it very slowly, harder, 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 until one of the string is going to break. What I want you to do with your neighbor is see if you can predict which of the two strings, the top or the lower, will be the one to break if I gradually pull it harder, harder, harder until snap-a-rooney. Talk it up. Let's try it, gang. How many say the top string's going to break because he's got the other string here ready for the next trial on the top? Good deduction. Let's try it. Watch this. It was the top. HC. Weight or inertia come into play. Weight. Very good. Let's look at this on the board. Okay. Now, I'm pulling down. I'm pulling with a force. Sets up a tension in there, doesn't it? In fact, I could go like that and it would sort of twang like a guitar string. Sets up a tension force, doesn't it, right? But isn't this tension force also transmitted up to the top string? If that's all the thinking we did, we would say, well, you have just as much tension in the lower string as the upper string. It's probably 50-50. Either one could break. Can you see there's something else to consider, though? Begins with a W, ends with a T. Weight. Okay, get that? This weight of this ball acts on which string? Only the top? Yes, only the top. So in addition to the tension that you're providing by pulling, you have the weight of the ball on this string. Now I think you can see there's more combined tension on the top than the bottom, and sure enough, the top one breaks. There's where weight comes into account. The force of gravity helps to make the tension in this one greater than in this one. Now I'm going to do it again. Only this time, I'm going to whip it down very quickly. I'm going to ask this ball to accelerate downward at a rate greater than free fall. I'm going to whip down with an acceleration more than 10 meters per second square. And I want you to predict which string going to break. Check the neighbor right now. This is an easy one, isn't it? And what's it going to be, huh? Here we go. Bottom one. Okay? Now, what is at play here? Weight or inertia? Inertia. The tendency of this ball to remain at rest during that brief force doesn't let that tension get up here as readily, and so what happens? It happens down below. This ball is not going to whack, go down faster than free fall. Instead, it's a little lazy. Lazy is another word for inertia in a sense. So the lazy ball stays there, and the bottom string breaks, and the top one, in a sense, is absorbed from the shock that otherwise would result. Can you kind of see that? It's important that you do it quickly. When you're in the supermarket and you have those baggies there, okay? And they're all a roll of these things, huh? And you've got your arms loaded. Do you have to put it down, hold the bag, and tear? No. You can just whip, do it quickly, right? If you do it quickly, the bag will tear. What happens if you do it slowly? Okay. You got to do it quickly, okay? Now, I can show you this in a different way, a little bit more dramatic. Let's try it. I could have hung the anvil, for example, by the strings, but I'd have to have a very strong string to hold it, wouldn't I? And if the anvil were hanging there and I whipped it in the same way, that the bottom string would break, leave the top one, unbroken, huh? But instead of pulling on it, why don't I push on it? Let's suppose I put the anvil over here.
You're not going to throw it.
Okay. This got a lot of mass. Right now it's at rest. What's it tend to remain at? Begins with an R. Rest, okay? There's a hammer. Okay? Would you put your head under there? Answer begins with a Y. You're a believer, aren't you? Don't you believe in physics? You could put your head under there. You know why? This thing's at rest. You hit it, going to tend to stay at rest. Your head's okay. Okay? Can I have a volunteer put their head underneath there, huh? Okay, tell you what, I'll do it. Okay? Can I have a volunteer man the hammer? Okay? Okay?
Remember the rest.
Now, I'll tell you what we'll do is I won't put it in my head, I'll put it in my chest. Could you help us, please? Okay. Put it right here. Right here.
Oh, God.
Okay, sit down, please. Okay, gang, it's for science. Harder. You see the physics there? A body at rest tends to stay at rest. And the force was too brief, not strong enough to appreciably move this. A little bit of give. That's why I didn't put it in the head, okay? A little bit of give in the old stomach, and therefore everything is A-OK. Got it? With a hammer. Inertia with a hammer. Do you ever want to tighten the head of a hammer? How do you do that?
Hit the handle.
Hit the handle, that's right. It's like this. This might have been your first lesson in inertia. Remember when you were a kid and this part of the hammer was loose and you were going like this to get it, make it tighter, and old Uncle Harry walked by and Uncle Harry said, no, there, child, you don't do it that way. And Uncle Harry said, you do it like this. That will tighten the hammerhead much better. And you looked at Uncle Harry and you said, HC. How come, right? And old Uncle Harry said, what did Uncle Harry say? Didn't Uncle Harry call your attention to the inertia of the mass, the metal part up here? Doesn't this have more mass than the handle? And didn't Uncle Harry say that when you get a lot of mass moving, it's going to tend to keep on moving? And when the handle is stopped by the thing below, doesn't that matter? Tend to keep right on going? Isn't that the law of inertia? A body in motion tend to stay in motion, and then that scrunch right on there? And so you do it that way, and don't we all do it that way? And when you do it that way, aren't you calling into play your idea that things that are moving tend to keep moving? And the more massive they are, the more that tendency, huh? Isn't it like driving two cars over some railroad tracks? One's a Cadillac and one's a Volkswagen, and you got a crate of eggs in the back seat? How many say same? You drive that Volkswagen, not very much mass, over the tracks. Okay. How about the old Caddy? Right on over. Okay. A body in motion with a lot of mass tend to keep right on going. Smaller one too. But when a force interacts, then, hey, what happens? The one with the more mass tends to keep right on doing what it's doing. That's the law of inertia. On your driver's license, it mentions your height, how tall you are. Isn't that true? Some friend says to you, hey, how tall are you? What do you say? You say, do you want my morning height or do you want my evening height? True or false? Let me tell you something about you might not know. Did you know that you are taller in the morning than in the night? And did you know the reason for that has to do with inertia, today's topic? This hammerhead, if I keep hitting and hitting, won't it keep settling? Don't you have hammerheads back here in your backbone? Doesn't it consist of many bones, which are all separated by a little cartilage? And if I go like this, see that thing settle, especially if it had cartilage in there instead of wood, right? What do you suppose happened to you when you boom, 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 boom? You see what happened? You choom, choom, choom. At the end of the day, you're like this, okay? You get in your bed at nighttime and you all come back again, okay? You get up in the morning, you are taller. Now, how many say, oh, okay, what a smidgen? Am I talking about a smidgen or am I talking about many smidgens? Begin with M. Many. It's a lot. In fact, I got a project for you to do. And the project is to show you that it's not a small effect. You are quite a bit taller in the morning than in the night. And I want you to measure that. Tonight, when you go home, please remember to do this. When you go home tonight, barefoot, before you hit the sack, reach up on the wall and see if you can touch something. It's best if there's something that's just a little bit out of reach, like maybe a beam ceiling or a chandelier. Reach up to something you can't quite touch, okay? That's right. You just can't do it. Hit the sack. Morning time, get up, bare feet, reach up, boom, you'll find your hands are clamped right onto that thing. For real. Scout's honor, try it. You really are taller in the morning than the night. Has to do with what? Inertia. Yeah. Now we have two objects, both the same color. Almost the same color. Okay? What I'm going to do is I'm going to belt these things with a hammer, and let's see how they respond. Which of these has the greater mass? Which, interestingly, brings us to a point. Some people think that how much mass is how big. Something with a lot of mass has to be big, like a big pillow. And something that's small can't be very massive, like an automobile battery. See? How much matter is in something and how much space it takes up are different ideas. Don't confuse mass with volume, because these have the same volume, but they have a different amount of matter. Watch this. When I hit the top one, now I hit the bottom one. Okay, huh? Would you dare put your head over here while I hit it? NWB, right? No way, baby, okay? But how about this one here? Would you put your head there? Sure. You see that? Has a lot of mass. Now, what's the reason that this one didn't respond and this did?
That one weighs more?
No, this is a little lighter color. You see that? Can you see it's a different shade of gray? Okay? So it's the color that counts, right? Okay? True or false? Tilt or no tilt? Tilt. Okay, it's the amount of matter involved. You can see this is wood and this is iron. Same size, same volume, even same-ish color, but different amount of material, different amount of mass. And this sort of thing would behave just the same way if I were in a place with stronger gravity, weaker gravity, or no gravity at all. So don't say that mass and weight are the same thing. Something with mass has weight if it's in a gravity region, a gravitational field on a planet's surface or something like that. But the amount of matter in an object is independent of that. It's fundamental. It has to do with the matter that's in there regardless of its location in the universe. Difference between the two. Any questions? Now, so far we've been talking about objects at rest mainly. Objects at rest tend to remain at rest. Turns out that objects that are moving tend to remain moving anyway. And this idea was not acknowledged by people about 400 years ago when Copernicus announced that the Earth revolves around the sun. And the whole idea that the Earth moves was so revolutionary, shook the foundations of reason with many, many people. Not the foundations of reason, but maybe the foundations of faith and other ideas. How can the Earth possibly be moving, it was argued. Calculations were made. If it was true that the Earth was moving around the sun, as Copernicus suggested, then the Earth would have to be moving at more than 100,000 kilometers per hour. 100,000 kilometers per hour. That's about 30 kilometers per second. Here was one of the arguments that went against the idea that the Earth could possibly move. And it's this. Consider a field, tree, tall tree. At the top of the tree, a bird. Underneath the bird, a fat, juicy worm burrows up from the ground. Bird food. Bird's at the top of the tree, sees the worm below, drops from the tree, boom, grabs the worm, flies back up to the tree. Can that happen? Yes, it can. And it was argued the fact that that is a common happening is evidence that the world cannot move. Because if the world was moving at 30 kilometers per second, and that bird lets go of the branch and takes a second to get down below, then that worm swept 30 kilometers away. And a bird could not go 30 kilometers in 1 second. Therefore, the Earth does not move. The Earth, my friend, is at rest. Now, what would you say to counter that argument? I want you to think about that, okay? Later.